Astronomy is the oldest of the natural sciences, dating back to antiquity, with its origins in the religious, mythological, cosmological, calendrical, and astrological beliefs and practices of prehistory. Vestiges of these are still found in astrology, a discipline long interwoven with public and governmental astronomy, and not completely disentangled from it until a few centuries ago in the Western world. In some cultures, astronomical data was used for astrological prognostication. Ancient astronomers were able to differentiate between stars and planets, as stars remain relatively fixed over the centuries while planets will move an appreciable amount during a comparatively short time. Early history. Early cultures identified celestial objects with gods and spirits. They related these objects to phenomena such as rain, drought, seasons, and tides. It is generally believed that the first astronomers were priests, and that they understood celestial objects and events to be manifestations of the divine. Hence early astronomy's connection to what is now called astrology. Ancient structures with possibly astronomical alignments probably fulfilled astronomical, religious, and social functions. Calendars of the world have often been set by observations of the sun and moon, and were important to agricultural societies, in which the harvest depended on planting at the correct time of year. The most common modern calendar is based on the Roman calendar, which broke the traditional link of the month to the phases of the moon and divided the year into 12 months, alternately comprising 30 and 31 days. In 46 BC, Julius Caesar instigated calendar reform and adopted what is now known as the Julian calendar, based upon the 3,651 quarters day year length originally proposed by the 4th century BC Greek astronomer Callippus. Prehistoric Europe. Since 1990, our understanding of prehistoric Europeans has been radically changed by discoveries of ancient astronomical artifacts throughout Europe. The artifacts demonstrate that Neolithic and Bronze Age Europeans had a sophisticated knowledge of mathematics and astronomy. Among the discoveries are the Warrenfield calendar in the Dee River Valley of Scotland's Aberdeenshire, first excavated in 2004 but only in 2013 revealed as a find of huge significance. It is to date the world's oldest known calendar, created around 8000 BC and predating all other calendars by some 5000 years. The calendar takes the form of an early Mesolithic monument containing a series of 12 pits which appear to help the observer track lunar months by mimicking the phases of the moon. It also aligns to sunrise at the winter solstice, thus coordinating the solar year with the lunar cycles. The monument had been maintained and periodically reshaped, perhaps up to hundreds of times, in response to shifting solar-lunar cycles over the course of 6,000 years, until the calendar fell out of use around 4,000 years ago. Goseck Circle is located in Germany and belongs to the linear pottery culture. First discovered in 1991, its significance was only clear after results from archaeological digs became available in 2004. The site is one of hundreds of similar circular enclosures built in a region encompassing Austria, Germany, and the Czech Republic during a 200-year period starting shortly after 5000 BC. The Nebra sky disk is a Bronze Age bronze disk that was buried in Germany, not far from the Goseck Circle, around 1600 BC. It measures about 30 centimeters diameter with a mass of 2.2 kilograms and displays a blue-green pattern or inlaid with gold symbols. Found by archaeological thieves in 1999 and recovered in Switzerland in 2002, it was soon recognized as a spectacular discovery, among the most important of the 20th century. Investigations revealed that the object had been in use around 400 years before burial, but that its use had been forgotten by the time of burial. The inlaid gold depicted the full moon, a crescent moon about 4 or 5 days old, and the Pleiades star cluster in a specific arrangement, forming the earliest known depiction of celestial phenomena. 12 lunar months pass in 354 days. requiring a calendar to insert a leap month every 2 or 3 years in order to keep synchronized with the solar year's seasons. The earliest known descriptions of this coordination were recorded by the Babylonians in 6th or 7th centuries BC, over 1,000 years later. Those descriptions verified ancient knowledge of the nebulous sky disk's celestial depiction as the precise arrangement needed to judge when to insert the intercalary month into a lunisolar calendar, making it an astronomical clock for regulating such a calendar 1,000 or more years before any other known method. The Kokino site, discovered in 2001, sits atop an extinct volcanic cone at an elevation of 1,013 meters, occupying about 0.5 hectares overlooking the surrounding countryside in the Republic of Macedonia. A Bronze Age astronomical observatory was constructed there around 1900 BC and continuously served a nearby community that lived there until about 700 BC. The central space was used to observe the rising of the sun and full moon. 3 markings locate sunrise at the summer and winter solstices and at the 2 equinoxes. 4 more give the minimum and maximum declinations of the full moon, in summer, and in winter. 2 measure the lengths of lunar months. Together, they reconcile solar and lunar cycles in marking the 235 lunations that occur during 19 solar years, regulating a lunar calendar. On a platform separate from the central space, at lower elevation, 4 stone seats were made in north-south alignment, together with a trench marker cut in the eastern wall. This marker allows the rising sun's light to fall on only the second throne. At midsummer, it was used for ritual ceremony linking the ruler to the local sun god, and also marked the end of the growing season and time for harvest. Golden hats of Germany, France and Switzerland dating from 1400 to 800 BC are associated with the Bronze Age Urnfield culture. The golden hats are decorated with a spiral motif of the sun and the moon. They were probably a kind of calendar used to calibrate between the lunar and solar calendars. Modern scholarship has demonstrated that the ornamentation of the gold leaf cones of the Schifferstadt type, to which the Berlin gold hat example belongs, represent systematic sequences in terms of number and types of ornaments per band. A detailed study of the Berlin example, which is the only fully preserved one, showed that the symbols probably represent a lunisolar calendar. The object would have permitted the determination of dates or periods in both lunar and solar calendars. Mesopotamia. The origins of Western astronomy can be found in Mesopotamia, the land between the rivers Tigris and Euphrates, where the ancient kingdoms of Sumer, Assyria, and Babylonia were located. A form of writing known as cuneiform emerged among the Sumerians around 3500–3000 BC. Our knowledge of Sumerian astronomy is indirect, via the earliest Babylonian star catalogues dating from about 1200 BC. The fact that many star names appear in Sumerian suggests a continuity reaching into the early Bronze Age. Astral theology, which gave planetary gods an important role in Mesopotamian mythology and religion, began with the Sumerians. They also used a sexagesimal place value number system, which simplified the task of recording very large and very small numbers. The modern practice of dividing a circle into 360 degrees, of 60 minutes each, began with the Sumerians. For more information, see the articles on Babylonian numerals and mathematics. Classical sources frequently use the term Chaldeans for the astronomers of Mesopotamia, who were, in reality, priest-scribes specializing in astrology and other forms of divination. The first evidence of recognition that astronomical phenomena are periodic and of the application of mathematics to their prediction is Babylonian. Tablets dating back to the Old Babylonian period documents the application of mathematics to the variation in the length of daylight over a solar year. Centuries of Babylonian observations of celestial phenomena are recorded in the series of cuneiform tablets known as the Enuma Anu Enlil. The oldest significant astronomical text that we possess is Tablet 63 of the Enumera Anu Enlil, the Venus tablet of Ammisaduqa, which lists the first and last visible risings of Venus over a period of about 21 years and is the earliest evidence that the phenomena of a planet were recognized as periodic. The Mul Apan contains catalogues of stars and constellations as well as schemes for predicting heliacal risings and the settings of the planets, lengths of daylight measured by a water clock, gnomon, shadows, and intercalations. The Babylonian Gu text arranges stars in strings that lie along declination circles and thus measure right ascensions or time intervals, and also employs the stars of the zenith, which are also separated by given right ascensional differences. A significant increase in the quality and frequency of Babylonian observations appeared during the reign of Nabonassar. The systematic records of ominous phenomena in Babylonian astronomical diaries that began at this time allowed for the discovery of a repeating 18-year cycle of lunar eclipses. For example, the Greek astronomer Ptolemy later used Nabonassar's reign to fix the beginning of an era, since he felt that the earliest usable observations began at this time. The last stages in the development of Babylonian astronomy took place during the time of the Seleucid Empire. In the 3rd century BC, astronomers began to use goal-year texts to predict the motions of the planets. These texts compiled records of past observations to find repeating occurrences of ominous phenomena for each planet. About the same time, or shortly afterwards, astronomers created mathematical models that allowed them to predict these phenomena directly, without consulting past records. A notable Babylonian astronomer from this time was Seleucus of Seleucia, who was a supporter of the heliocentric model. Babylonian astronomy was the basis for much of what was done in Greek and Hellenistic astronomy, in classical Indian astronomy, in Sasanian Iran, in Byzantium, in Syria, in Islamic astronomy, in Central Asia, and in Western Europe. India. Astronomy in the Indian subcontinent dates back to the period of Indus Valley Civilization during 3rd millennium BCE, when it was used to create calendars. As the Indus Valley Civilization did not leave behind written documents, the oldest extant Indian astronomical text is the Vedanga Jyotisha, dating from the Vedic period. Vedanga Jyotisha describes rules for tracking the motions of the sun and the moon for the purposes of ritual. During 6th century AD, astronomy was influenced by the Greek and Byzantine astronomical traditions. Aryabhata, in his magnum opus Aryabhatiya, propounded a computational system based on a planetary model in which the Earth was taken to be spinning on its axis and the periods of the planets were given with respect to the Sun. He accurately calculated many astronomical constants, such as the periods of the planets, times of the solar and lunar eclipses, and the instantaneous motion of the Moon. Early followers of Aryabhata's model included Varahamihira, Brahmagupta, and Bhaskara II. Astronomy was advanced during the Shunga Empire and many star catalogues were produced during this time. The Shunga period is known as the Golden Age of astronomy in India. It saw the development of calculations for the motions and places of various planets, their rising and setting, conjunctions, and the calculation of eclipses. Bhaskara II was the head of the astronomical observatory at Ujjain, continuing the mathematical tradition of Brahmagupta. He wrote the Siddhanta Shiromani, which consists of 2 parts, Goladhyaya and Grahaganita. He also calculated the time taken for the Earth to orbit the Sun to 9 decimal places. The Buddhist University of Nalanda at the time offered formal courses in astronomical studies. Other important astronomers from India include Madhava of Sangama Grama, Nilakantha Somayaji and Jashtardhava, who were members of the Kerala school of astronomy and mathematics from the 14th century to the 16th century. Nilakantha in his Aryabhatiyabhasya, a commentary on Aryabhata's Aryabhatiya, developed his own computational system for a partially heliocentric planetary model, in which Mercury, Venus, Mars, Jupiter and Saturn orbit the Sun, which in turn orbits the Earth, similar to the Tychonic system later proposed by Tycho Brahe in the late 16th century. Nilakantha's system, however, was mathematically more efficient than the Tychonic system, due to correctly taking into account the equation of the center and latitudinal motion of Mercury and Venus. Most astronomers of the Kerala school of astronomy and mathematics who followed him accepted his planetary model. Greece and Hellenistic world. The ancient Greeks developed astronomy, which they treated as a branch of mathematics, to a highly sophisticated level. The first geometrical, three-dimensional models to explain the apparent motion of the planets were developed in the 4th century BC by Eudoxus of Cnidus and Callippus of Cyzicus. Their models were based on nested homocentric spheres centered upon the Earth. Their younger contemporary Heraclides Ponticus proposed that the Earth rotates around its axis. A different approach to celestial phenomena was taken by natural philosophers such as Plato and Aristotle. They were less concerned with developing mathematical predictive models than with developing an explanation of the reasons for the motions of the cosmos. In his Timaeus, Plato described the universe as a spherical body divided into circles carrying the planets and governed according to harmonic intervals by a world soul. Aristotle, drawing on the mathematical model of Eudoxus, proposed that the universe was made of a complex system of concentric spheres, whose circular motions combine to carry the planets around the Earth. This basic cosmological model prevailed, in various forms, until the 16th century AD. In the 3rd century BC, Aristarchus of Samos was the first to suggest a heliocentric system, although only fragmentary descriptions of his idea survive. Eratosthenes, using the angles of shadows created at widely separated regions, estimated the circumference of the Earth with great accuracy. Greek geometrical astronomy developed away from the model of concentric spheres to employ more complex models in which an eccentric circle would carry around a smaller circle, called an epicycle, which in turn carried around a planet. The first such model is attributed to Apollonius of Perga, and further developments in it were carried out in the 2nd century BC by Hipparchus of Nicaea. Hipparchus made a number of other contributions, including the first measurement of precession and the compilation of the first star catalogue, in which he proposed our modern system of apparent magnitudes. The Antikythera mechanism, an ancient Greek astronomical observational device for calculating the movements of the Sun and the Moon, possibly the planets, dates from about 150–100 BC, and was the first ancestor of an astronomical computer. It was discovered in an ancient shipwreck off the Greek island of Antikythera, between Kythera and Crete. The device became famous for its use of a differential gear, previously believed to have been invented in the 16th century AD, and the miniaturization and complexity of its parts, comparable to a clock made in the 18th century. The original mechanism is displayed in the bronze collection of the National Archaeological Museum of Athens, accompanied by a replica. Depending on the historian's viewpoint, the acme or corruption of physical Greek astronomy is seen with Ptolemy of Alexandria, who wrote the classic comprehensive presentation of geocentric astronomy, the Megalsyntaxis, better known by its Arabic title Almagest, which had a lasting effect on astronomy up to the Renaissance. In his planetary hypotheses, Ptolemy ventured into the realm of cosmology, developing a physical model of his geometric system, in a universe many times smaller than the more realistic conception of Aristarchus of Samos 4 centuries earlier. Egypt. The precise orientation of the Egyptian pyramids affords a lasting demonstration of the high degree of technical skill in watching the heavens. attained in the 3rd millennium BC. It has been shown the pyramids were aligned towards the pole star, which, because of the precession of the equinoxes, was at that time Thuban, a faint star in the constellation of Draco. Evaluation of the site of the Temple of Amun-Re at Karnak, taking into account the change over time of the obliquity of the ecliptic, has shown that the Great Temple was aligned on the rising of the midwinter sun. The length of the corridor down which sunlight would travel would have limited illumination at other times of the year. Astronomy played a considerable part in religious matters for fixing the dates of festivals and determining the hours of the night. The titles of several temple books are preserved recording the movements and phases of the sun, moon and stars. The rising of Sirius at the beginning of the inundation was a particularly important point to fix in the yearly calendar. Writing in the Roman era, Clement of Alexandria gives some idea of the importance of astronomical observations to the sacred rites. And after the singer advances the astrologer, with a horologium in his hand, and a palm, the symbols of astrology. He must know by heart the Hermetic astrological books, which are 4 in number. Of these, 1 is about the arrangement of the fixed stars that are visible, 1 on the positions of the sun and moon and 5 planets, 1 on the conjunctions and phases of the sun and moon, and 1 concerns their risings. The astrologer's instruments are a plumb line and sighting instrument. They have been identified with 2 inscribed objects in the Berlin Museum, a short handle from which a plumb line was hung, and a palm branch with a sight slit in the broader end. The latter was held close to the eye, the former in the other hand, perhaps at arm's length. The Hermetic books which Clement refers to are the Egyptian theological texts, which probably have nothing to do with Hellenistic Hermetism. From the tables of stars on the ceiling of the tombs of Ramesses VI and Ramesses IX, it seems that for fixing the hours of the night a man seated on the ground faced the astrologer in such a position that the line of observation of the pole star passed over the middle of his head. On the different days of the year each hour was determined by a fixed star culminating or nearly culminating in it, and the position of these stars at the time is given in the tables as in the center, on the left eye, on the right shoulder, etc. According to the texts, in founding or rebuilding temples the north axis was determined by the same apparatus, and we may conclude that it was the usual one for astronomical observations. In careful hands it might give results of a high degree of accuracy.